Hello and welcome to a new season of the Oxford Online Maths Club. My name's James. I work at the University of Oxford doing some admissions and outreach and teaching. And this series is our chance to show you some mathematics. Whoever you are, wherever you're watching, anyone can join in. We are broadcasting live to YouTube and the videos are going to be recorded and they're going to stay on YouTube where they'll live alongside about 50 other episodes that we've done over the last couple of years. We started doing this back when everyone was doing things online and we've kept doing them. So welcome to another season of Oxford Online Maths Club. If it's your first time joining, then great to have you with us. We're going to do some maths this term. The idea is that later on we'll have some actual Oxford students involved as well, showing you some of their favourite maths. I haven't got one today because term hasn't started yet, so at the moment the building's really quiet, there are no students around at the moment. Maybe your term has already started, but for our university students they're not back yet. So at the moment it's just me. I'm going to do today's maths club session with you, and hi to everyone in chat. Really good question. So hi, I can see Kai is in chat. I saw Gauss in chat earlier on. Other people are anonymous. I'm going to suggest if you want to join chat, there is a link on screen if you're watching on mobile or something, and maybe you've got a second device or some clever mobile phone solution for being in two places at once on the internet. You can open that. Chat this term is powered by Vvox, so if you head into Vvox you can post in chat over there. We like Vvox compared to YouTube chat because for YouTube chat you need to make a Google account. For Vvox you can be completely anonymous, so no one will know who you are unless you sign off. I use a little tag caret shape thing above the 6 key for my sign-offs. You can use a dash or just put your name at the end. You don't have to. Let's see what Gauss and Jack are doing. Hi Jack, good to see people. Good to see people here as well from the Mat live stream which we ran last term. The difference here is that we're probably not going to talk about maths if we can avoid it. And there's a good question there about joining in. Do you need a bit of paper? I'm going to recommend that you get a bit of paper. A little bit more about how you might join in with the Maths Club in a moment, but I'm going to recommend that you get a bit of paper and a pen or pencil or something. Will wants to know if they need paper and pen and calculator. I suggest, yeah, paper and pencil might be handy for this particular one. I'd like to make these interactive. The interaction is a little bit tricky because you can see me, you can see what I'm writing on the screen. I can only see what you put in chat. So if nobody turns up to chat, then it's pretty lonely for me. Hi Ben as well. Yeah, M double star. Wow, it took some decoding. Hi people in Poland and Ukraine. My goodness. Oh my goodness, 120 hours until it's. Oh right, okay. We're also trying not to talk about Oxford admissions too much. Here is an Oxford admissions question straight away. People know that my job involves Oxford admissions, so people like to ask admissions questions. Yeah, we've always had a bit of a global reach, but it's always great to watch by people around the world. So I should say about joining in. So my hope is that we do interactive things, that we have things where you can join in chat, or at least you can try something at home. I'm aware the screen is currently blank, but maybe in a minute we'll have something to do at home. If you're watching live, you could join chat to join in. If you're watching the recording, then you're welcome to post a comment. We might not see all of the comments underneath on YouTube. Or you can contact us to show us what you've been up to. We've got an email address, a dedicated email address for the Maths Club, OOMC, at maths.ox.uk. That's also on screen, and there's a link in the YouTube description as well to get us in. Petition for... Yeah, where is it? Yeah, chat is different from last time. Is it going to be hard? I hope it's not going to be too hard. I hope that we've got something for everyone. We haven't set an upper limit on what people are allowed to talk about. I've been talking to students about what they want to present this term. I'm really excited. And there's no upper limit to what they want to talk about, but they know that they're talking to everyone. So it's not the same as them talking to each other about the courses that they're doing. They know that they're talking to everyone. Good. Okay, petition for a TikTok. I have a TikTok. I don't use it very much. Is this a petition for me to get back on TikTok? Oh gosh, forcing me to learn how to use TikTok again. Different chat this term. It's complicated. If you want a presentation about IT procurement at the University of Oxford, then fine. This session is 1 hour long, and what's it going to be about? What's it going to be about? Let's find out now using technology on screen. I haven't done this for about 6 months. I really hope it works. Coming up. Yeah! Coming up today, triangles. I want to tell you about my favourite triangle. I'm a big fan of lots of different triangles. Suggestions for triangle facts in chat, please, if you've got a favourite triangle fact or things you like about triangles. Maybe you've got a favourite triangle, let us know in chat. And we're going to be talking about my favourite triangle. Fitbit thinks I've just hit my step goal by enthusiastically gesturing about triangles, which is a new one for me. We're also going to talk about robots, but I should put a caveat on that we're going to talk about very stupid robots. We're going to talk about possibly the most stupid robot one can possibly imagine. So we'll get in there as well. Bracketify. Bracketify is a term that Gauss wanted me to use last term, and I managed it a little bit, but kept forgetting. Good, right, triangles are shapes and have three corners. There's an effect in chat as well that if somebody says something really clever in chat, then it can feel like you don't have anything to add, and you should try and overcome that a bit. Even if someone says something really clever, like triangles are shapes, you should still feel welcome to join in. I want to hear from lots of different people and lots of different answers, or even just the same answer lots of times. Rulu triangle is a very good triangle. That is a very good triangle. Do you want to drop whoever said Rulu triangle? Do you want to put? I think there's a character limit, but you want to put like a one sentence of what is a Rulu triangle? I mean, we could all go and Google it, but maybe I think it might be fun for you to put like one sentence of what's a Rulu triangle. I see Kai wants to know what a Rulu triangle is as well. Triangle is a very strong shape, says JB. Yeah, cool. Okay, not all triangles. Triangles on other surfaces. Good. Right. Okay. Am I going to do bracketify? Is this comment bracketified, or is it in parentheses? Right. Good. Okay. These are some good triangle facts. So the triangles are 2D fact is kind of directly contradicting the angle sum of 180 degrees fact that somebody else has put in as well. Cool. Okay. That was fun. Let's make that go away. Good. Right. Whiteboard. Or a slightly off whiteboard. Perfect. Is that how you say Rulu? Right. Hang on. You should not learn pronunciation from me. I don't even know how to pronounce the word pronunciation. So, you know. Degenerate triangles. They sound exciting, but they're just triangles with no area because they're a line, because one of the points lies on that point. Hi Marcus, I should stop revising for the math. You're already revising for maths because you're already learning maths. At the moment, focus on learning maths. It's a curved triangle with constant width. That's a pretty good description. And we got votes for Sierpinski triangles and Pascal's triangle. Kai, who previously gave us triangles have three corners, hitting us again with the hard facts that triangles are also instruments. Right, Pascal's triangle's got several votes. I do want to talk about Pascal's triangle. It is my favourite triangle. There's a chance that you already know everything about Pascal's triangle, in which case you've already seen some of this before, I suppose. If you came to a Maths Week England session last term with me, then I did some stuff about Pascal's triangle there as well, but almost nobody did. So unlikely to be overlap there between those two particular sessions. Shall I stop waffling and start doing Pascal's triangle? Pascal's triangle works like this. It has two ones at the top. Actually, people sometimes put another one right at the top up here, but I'm going to start with two ones. Makes it slightly easier to talk about. And then the next row down, you take those ones, you copy them, spreading outwards, but here, in between and underneath, you write the sum of the numbers above. So 1 plus 1 is 2. Welcome to the Oxford Online Maths Club. The number here is 2. Okay. I really hope that makes sense, but just in case, I'm going to demonstrate what happens next. So next, these ones keep spreading outwards. They're going to form the outside of our triangle, but inside the triangle, what we do is we add together the numbers above. So here 1 plus 2 is 3, 2 plus 1 is also 3. So we add those together and get some 3s. Good, okay, I'm going to keep going. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and this 1 over here stays as a 1. And if it's okay with you, I'm now going to erase the arrows so that we can just look at the numbers, because it's really the numbers that I'm interested in. Mathematician, very interested in the numbers. These ones in particular. Okay, how are we doing? We're getting some more numbers in. If you've got a pen and paper, you can probably do this sort of thing faster than me. I bet you're faster at adding together. My maths block is tomorrow, lol. What am I doing? Watching James draw Pascal's Triangle. Revision, I guess. Revision of stuff. I can't really remember when you learn about this. Prisma's not here today. We're doing chat. Prisma might be back later in term, but we're out of time. Prisma is a chat regular. Normal advice about trying not to contact strangers you've met on the internet. I'm aware that there is some sort of Discord, but yeah, be careful everyone. Right, okay. Okay, we've got some numbers, we're still going. We're in year 12, it's on A level, an AQA level 2 further maths, but not GCSE, so maybe not revision. Okay, if this is not revision for you, even better, learning some new numbers. If you're doing A level maths, you've probably seen these numbers before, because they are the same numbers, maybe you've already realised, they're the same numbers that you get from polynomials, from that bit of maths to do with binomial expansions, if that means anything to you, and don't worry if that doesn't mean anything to you. So you also get these numbers somewhere else. And now, if you've got your own bit of paper and pencil, you've probably generated way more of this than me. I would like to point out some patterns in Pascal's Triangle. Maybe you can already see some patterns in Pascal's Triangle. There are quite a lot that you might spot. The reason I want to do this is that calculating, doing the addition is fine, but actually interpreting what you can see and generating patterns is kind of interesting. Oh yeah, okay. So what does it have to do with binomial expansion? Let's put that down as a pattern. I'm going to go over here. So if you imagine the polynomial 1 plus x, which has just been suggested, thank you, anonymous person who put 1 plus x to the end, thank you very much. If you work out 1 plus x squared, then you'll find that it looks a little bit like this. I'm being vague. I'm being vague to try and provoke you into doing this at home. I like you to try and work out these things, and you should find they look a little bit similar. Someone said never understood how the terms correspond, so maybe we should think about that a little bit as well. It's not a coincidence that the numbers you get when you do these expansions, multiplying out all these brackets, the numbers that you get are the same as the numbers that you get in Pascal's Triangle. Yeah, people are describing patterns they can see in Pascal's Triangle. So we've got a couple of directions we could go here. We could dig deeper into why, which is a question that mathematicians love to ask and love to answer if we can. Why do these binomial coefficients, the things that you get when you multiply out polynomials, why do they match up with these numbers in Pascal's Triangle that I've got just by adding together small numbers? Be a good idea to explain that, to understand that, because adding small numbers together is really easy, polynomials are a bit harder. Yeah, okay, here's a description, I like this. The numbers also represent, I'm going to come back to this as well. Each coefficient of Pascal's Triangle is the Pascal's Triangle level, and the power drops off from the left from one term and increases to the left from the other. Okay, so these correspond to the different coefficients for different powers of x. I kind of agree. What are we trying to work out? We're trying to work out why the numbers are the coefficients of these powers, which is maybe something you were told at some point. Let's multiply this one out, just to be really clear about what I'm saying. Oh my goodness, where's that drawn a line? Okay. New year, new technology. The coefficients of 1 plus 2x plus x squared are 1, 2, and then sort of secretly a 1 in here as well. Those are the numbers in Pascal's Triangle. The coefficients of 1 plus x all cubed are this. Trust me, I've done some multiplication in my head or whatever. And that's 1331, so it matches up. Maybe that's something you've been told at A-level, or maybe it's something you've noticed, maybe you've never seen this before. But either way, I'd like to try and think about why that's true. Yeah, so this is why sometimes people put 1 at the top of the Pascal's Triangle, and I agree with JB, sometimes people think of this as 1 plus x to the power of 0 being the number 1. Maybe that's a helpful thing to think about, who knows. Yeah, people know some NCR stuff. So if you know the definition of binomial coefficients, then if you know the definition of how to expand these things on the right hand side. Oh, can you see where I'm pointing? Maybe you can't. You can not see where I'm pointing, right? You can't see my mouse. I'm going to try and switch that on. If you can see, if you know the definition of binomial coefficients, then you know the expansion of that involves these things with factorials in. Some people call them NCR, choosing function, and that's the same thing that appears in Pascal's triangle. So you've sort of seen that these are the same. So I suppose I'm wondering why the things match up. There's the mouse. There we go. Now I can point. There we go. Sorry, I was pointing at loads of things before, and I guess that was nonsense. Teething issues, start of the new year. Have I unmuted? Probably unmuted. You would tell me if I was on mute, right? Okay. Yeah. So it works like how these are also a bit like powers of 11, which, by the way, is a special case of subbing in x equals 10 into all of this on the right-hand side. Subbing in x equals 10 gives you powers of 11 on the right-hand side, and also the coefficients become digits. It works for a bit, and then it sort of stops working when you run out of digits. Don't overthink that. Good, right. Yeah, so binomial. I like these descriptions that are coming in, and I've given it a minute. If you put something in a minute ago, I've been waiting to get a few people to say similar things. These things are it's a bit like multiplying by 1 and also multiplying by x. So if we think of this as 1 plus 1 times x, and this is 1 plus 2x plus 1 times x squared, just to sort of make it really clear how they line up, we're thinking about these expressions. Then when you multiply by 1, it's a bit of a strange thing to do, but if you multiply by 1, that would just be rewrite your polynomial over here. So rewrite whatever's in that row, rewrite it down here. Whereas multiplying by x would be to move things this way. So take this x and multiply by x to get x squared, take this 1 and multiply by x to get another x. And then what you do is you simplify terms by adding them together. Yeah, so what this person says. Oh, it's Kai. I have to skim down to the bottom to see the name. To get from 1 plus x squared to 1 plus x cubed, you multiply that by 1 plus x, which means multiplying by x, and also multiplying by 1, and then adding things together. So over here I get x squared, and I get x cubed. Over here I get 2x squared, and I get 2x. Over here I get 1 times x is x, 1 times 1 is 1. Welcome to the Oxford Online Maths Club. Good, right, okay. Did we need to write all of that? Probably not. Probably you can see in your mind's eye or something, if you can visualize these things, probably you can see the way that the polynomial multiplication shifts things around by multiplying by x. Maybe you can sort of see it in your, I'm saying mind's eye a lot, which it's not actually how everyone thinks, but it's how some people think, that you can sort of see the 1 staying here and also a second shadow copy of this being multiplied by x and going kind of this way. I don't know. Maybe that's just me. Maybe I'm sort of seeing ghosts and nobody else can see these things shifting around and adding together. Who knows? Some of the stuff I write is just because things are happening in my head, and it's not really okay for me to just have things happening in my head that I don't put down. Yeah, learning about aphantasia. Aphantasia is a complicated thing. Yeah, okay, right, good. People know about binomial. Right, okay. Let's talk about other patterns that people spotted, because I saw other things going on in chat. I'm going to erase all of this light blue stuff. So I saw people naming patterns. Someone said the triangle numbers appear in Pascal's triangle, and you are correct. Let's have a quick point. Have a quick point? What on earth? That's not words. There are some triangle numbers over here. Do people know what triangle numbers are? Let me know in chat if you'd like a reminder of how triangle numbers work. Why do I use X in algebra? I think it sort of stands for mystery, right? The unknown quantity, the X factor. I don't know the history. I should learn history next. Okay, right. No, that makes a triangle, like how 1 plus 1 plus 1. Sorry, yeah, it's really hard to describe triangles in chat, isn't it? Because you can't draw the little picture. 1 plus 1 plus 1 is 3. Yeah, you have to stack them. You have to stack them to get like a triangle, like you're about to play snooker and you're lining up the balls for snooker. I've played snooker once, right? You have approximately 15 or maybe 10 of them, or possibly as many as 21, but it's one of these numbers of how many there are, plus the extra one, the kind of white cue ball that sits over there being its own very small triangle down the other end of the table. And then the way you play snooker is you accelerate the first triangle towards the large triangle, and see what happens. Good, that was a really great description, James. Brilliant. Triangle numbers. It is a quadratic sequence. If you've learned about quadratic sequences at school or college, then here's an example of one. Would you like to see a cubic sequence? You do not learn about cubic sequences in school or sixth form, but here is one. Does anyone know these numbers? It's a bit like factorial numbers, but adding instead of multiplying. Yes, it's 1 plus 2 plus 3 instead of 1 times 2 times 3. It's almost a shame that we have this snazzy notation for factorial, multiplying, but not a snazzy number for the triangleification. It could be like that. Nobody does this. This is original research in this corner. These are pyramid numbers. It's an example of a cubic sequence. Cubic sequence is not a very common phrase. I don't think I've invented it, but it's the best description I've got for it. These ones are tetrahedron numbers. So that probably introduces as many questions as it answers, right? I mean, it answers the very literal question of what are these, but new questions, I mean, what are the tetrahedron numbers? What's a tetrahedron? What's a number? No, we know what a number is, more or less. The differences are triangle numbers. Yeah, the differences are triangle numbers. That's sort of something that Pascal's triangle does for us, because along the way, to get from this number to the next one, we're adding on this triangle number. So Pascal's triangle is sort of calculating all the triangle numbers for us, and also, like a sort of factory process, adding them up as it goes along. So this diagonal has the sums of the triangles, just like the triangle numbers are the sums of the normal numbers. Thank you for this. The tetrahedral numbers are the sums of the triangle numbers. The thing to imagine is a stack of cannonballs. This is not quite how stacks of cannonballs actually work, never mind, but to imagine stacks like this, a triangle-based pyramid, this is not a great picture. This is the top, this is the middle, this is the base. There are 6 here, and 3 here, and 1 here. It's a stack of triangles. And 6 plus 3 plus 1 is 10. I regret saying what is a number, for the record. Is each diagonal a sequence of that power? Yes, it's something to do with that. Like, so if you think of this as a quadratic sequence, which somebody said in chat, so I'm riffing on that idea, I guess. If you think this is a quadratic sequence, then I suppose this is a cubic sequence. The next one is a quartic sequence. You would need things like, this is for sequence fans only, if you're a big fan of sequences, you would need things like n to the 4 and lower powers in order to describe this one. This sequence. It's n to the 4 divided by some number. Anyway, right. Sequence fans only. I'm actually erasing that straight away because it was too confusing. Even by my standards, too confusing. How do you spell quartic? You nailed it. That's brilliant. Is it that? Is it just 1/6 x plus 1, x plus 2? I should know that. Do you want to talk about that one? So, something I really like about these sequences is that each one is an example of a sort of abstraction. To take these examples of triangles or tetrahedrons, tetrahedra? Either's probably fine. To take these examples and to generalize them. Pascal's triangle carries on that calculation to add up all of these for us. So we're doing some sort of abstraction in this direction to go to the sort of nth degree down this way. But there's something else going on in this direction. Going down this direction, reading the diagonals, we have something else going on. Let's play the same game. This sequence, you can only see the first bit of it here. 1, 5, 15. The next one is 35. I think, yeah, it's one of the binomial coefficients that comes up if you do powers of 7. And if you have to do powers of 7, then I feel very sorry for you. These ones, oh dear. Somebody's just asked about a practical or useful application, just as I was about to say something about 4-dimensional pyramids. So that's a little bit awkward because I've been caught talking about 4D pyramids just as someone asked about useful or practical things. 4-dimensional pyramids are like a natural analogue of going beyond, like how you go from triangles to 3D tetrahedra. A 4D pyramid sort of structure would be a tetrahedron-based string of tetrahedrons of different sizes stacked together through the 4th dimension, which I'm illustrating the fourth dimension by stretching spaghetti in the air, but that's not a very useful metaphor. Yeah, gosh, am I getting some formulae in chat, which might be correct? Who knows? Homework, formulas for these. We sort of know a formula for these because of the link to the binomial coefficients. So if you've got some factorials going on, it's probably something with factorials. Seems all right to me. Interesting, but very confusing. That's the tagline. That's the tagline for not just today, but what's going on with maths. Because the surprise that maths keeps giving me is that something like this, where we've just been adding together small numbers, Pascal's Triangle, some of you have seen it in school already, contains within it a pattern for the number of dots in a four-dimensional tetrahedron-based pyramid. It's sort of like this really simple idea that contains with it infinite depth, or lots of different stuff going on under the surface. Interesting and confusing, even though it's even though it's kind of just adding together small numbers. If you think this is confusing, then I think you're right, because I just asked you to imagine a four-dimensional pyramid. Given more technology, imagine the sort of stuff we could build. Okay, where was I going with this? Oh yeah, the further diagonals are the further diagonals are higher dimensions. So the next one is down is 5D, but I think I should stop talking about higher dimensions. From live streams I've done before, there are sort of two running jokes. One is that we should always consider higher dimensions. That any result is more interesting if you go to higher dimensions. That's one of the running jokes we've had in other live streams. The other one is, of course, that we should look at complex numbers. Don't put pressure. Yeah, no, it's all right. We can do this. Good. Do you mean me, or is somebody putting pressure on somebody else? Please don't put pressure on each other in chat. I will happily take pressure to do things, but is the pressure for me to say bracketify? Because that's not going very well, is it? Right, good. Okay. Small break while I erase some doodles on top of Pascal's Triangle. There was that question about useful and practical, and I think it was from someone who suggested an actual useful practical use of Pascal's Triangle. Or if not, then there are two like-minded people in chat. Let's get rid of 35 as well. Because these represent the number of ways to get to a point if you move along a grid. Let's draw the grid in. So if I mark these as islands, and I'm going to join them up with roads, or pathways, or bridges. Actually, I always do roads. So I think today they're islands and bridges. To join these up with bridges like this, there are some puzzle games where you have numbers in circles joined up with bridges. This is a little bit like that, I suppose, but not quite. So these are actually, despite the fact that Pascal's Triangle is a triangle, this grid that I'm drawing is actually a grid of squares. They've been rotated 45 degrees, but don't let that deceive you. And the numbers are then the number of ways to get from the top square down to a target square, only going down the picture. So if you're not allowed to go up again, you want to go down. So let's say we want to get to this point over here. The number says there are 4 ways to do that. They look like this: down and then across, or you could fall down like this, or you could fall down like this, or you could fall down like this and end up over here. And the numbers track how many routes there are that fall down the board to that square. This is maybe useful for route planning if you live in a place that's full of squares, like I guess maybe New York. And it's also useful for a sort of statistics thing, where you have if you have some sort of random motion that's choosing whether to go left or right, but always falling down going left or right, then maybe it ends up in this sort of distribution. Maybe it ends up in this sort of distribution at the bottom. And something to look up is these sort of pegboards. These sort of pegboards where you have lots of ball bearings coming in at the top, and they bounce off these pegs like pachinko until they end up in some distribution at the bottom, mostly in the middle, but with some distribution that actually lines up quite nicely with the numbers that you get out of Pascal's triangle. So this is kind of practical application, that the numbers you get out of Pascal's triangle match up with what happens for random walks, which lines up with a lot of ideas in physics. Okay. Hooray! Brilliant. Okay, 15 squares, that's important. Is it 15 squares? The number of squares is a triangle number, right? Because the squares are arranged in a triangle. There's a square, and then 2, and then 3 squares, and then 4, and 15. So the number of squares is in Pascal's triangle. Pascal's triangle itself keeps track of how many... Anyway, brilliant, good, okay. There is some graph theory, I suppose, there, of the way that these things are linked together. But it's quite a... Graph theory sometimes looks at lots of different graphs and tries to prove things about lots of different graphs. Pascal's triangle, it's got one graph associated with it, I suppose. I want to do one more thing with Pascal's triangle. It's 5:30. I'm going to drink some water because it's halfway. What was Pascal's triangle originally for? That's a really good historical question. I think my aim, 2023, I think my aim is to learn more history of mathematics. I didn't learn very much history of mathematics during my degree course, partly by choice. I could have learnt more. I regret that. I should have learnt more. So 2023, new year, new me, history of maths, I guess. Right. Okay. I want to show you the... there we go. What was it for? So I have no idea, is my honest answer. But I also suspect that, from what I vaguely know about Pascal, that it doesn't need to have... it doesn't need to be for something that I think Pascal would have been happy if it wasn't for anything at all. It's just adding numbers together. I don't know, was it probably... I know Pascal did some early probability gambling sort of stuff. I sometimes say maths for the sake of maths, so I agree with that sentiment, maths for the sake of maths, but also maths is just there. So even without the sake of maths, this would sort of still exist. So it's nice that Pascal went and had a look at it, if indeed it's historically even true that Pascal went and looked at it. But even if Pascal hadn't gone to look at it, we would still have it. It would still sort of exist. That's a sort of weird thing about whether maths is invented or discovered, I suppose, which is a philosophical debate for another day. Did Pascal's triangle exist before Pascal? If we assume for a moment that Pascal existed and invented it. Sorry, that was unnecessarily controversial. It was for, people say it's for flipping coins. Thank you, chat. Thank you for that. Really quick, no citations, but really quick history research. And I guess the coin flipping thing is sort of related to those binomial probabilities that you maybe learn about in school. If you flip 6 coins, what's the probability that exactly 2 of them are heads? Anyway, so that's 15 out of 64 or something. Okay, one more thing with Pascal's triangle. If you've got your copy at home, I would like you to circle all of the odd numbers in Pascal's triangle. We've found all the triangle numbers. I mean, we found a line that reads like triangle numbers. Maybe we should try looking for the odd numbers. I'll do the first few. I found some odd numbers. There are some more. Over to you. If you've seen this before, you can let me know that you've seen it before. Don't spoil it for people who haven't seen this before. We're going to flip a lot of coins. If you flip one coin 50-50, you don't need any triangles or maths for that. If we're going to flip 6 coins, what's the probability that... You expect kind of about 3 of them to be heads. What's the probability that 2 or 3 or 4 of them are heads? I can imagine a world where kind of no one really knew how to do that calculation, but you've got to do something like that. We've seen this before. Okay, Nikita Mazepin has seen this before. Yeah, okay. Math can be fun for its own sake. Citation needed. It is really good, and my ambition here is that someone at home has got a bit of paper. They haven't seen this before. They're now circling the odd numbers in Pascal's triangle, and they've seen something new. That is my only hope for today. Right, good. And I'm hoping that it's the one person. I'm trying no spoilers while people are circling numbers at home. I'm hoping it's the one person who requested this. going to 7 and ignoring the 1s gives a happy face. That is a brilliant observation. Is it true? Oh, going to 7, so you want to go down to the 7s. Okay. Try that. Try this at home. And if you're watching the recording, would also be interested to see or hear from people if you haven't seen what happens before and you've tried it for the first time now. I'd like to hear from you. I'm not sure if someone said I didn't know this was in Pascal's Triangle. So one person's been surprised. I've gone down to the 7s. Oh, if you go down to the 7s, it's really interesting because there's loads of odd numbers down here. It's quite pretty. I've missed some, haven't I? I've missed some in the middle. Odd number over here. Or this one signed off as amazing. Or maybe that's just amazing. Kevin Magnussen has seen this before. There's also a running thing of people pretending to be Formula 1 drivers. So that's, yeah. One person who, didn't know it was here. I'm going to join the dots just to make it a little bit easier to see what's here. This is a triangle. Ooh. Do I want that one? I think I do want that one. Let's join the dots a bit. So you end up with this picture which has small triangles stacked together into larger triangles. So this small triangle at the top here is stacked together into these larger triangles like this in a sort of triforce shape like this. And then that shape is repeated and stacked together into 3 copies of itself underneath like that on the bigger scale. This bit, this bit is repeated down here in terms of the pattern. The numbers are different, but the odd even stuff is the same. It's also repeated over here. And then that whole pattern, can you guess what happens next? If you're calculating numbers, you can probably calculate numbers faster than me, but maybe you can see a sort of pattern here of how this maybe gets repeated. If you've seen this before, you probably can still come up with questions about what's going on. So other questions. I'm going to ask you some questions about it, but a skill that you might like to think about developing is coming up with your own questions. It's the thing that makes good mathematicians really great mathematicians if they're also coming up with their own hypotheses or ideas that they can improve. It means that your stuff comes out of nowhere from everyone else's point of view because you've invented a thing and proved it without people even expecting it. So here's some questions that I have when I see this. Does this keep happening forever? Does it keep stacking together? Marcus, that is a great question. Does it happen with multiples of different numbers? Marcus, you've set yourself some homework. If you want to try circling all the multiples of 5, I can see a whole bunch of multiples of 5 down here, and then a few more underneath maybe. I can't really see on this scale what's going on. If you want to try multiples of 17, no one's stopping you. That is a great follow-up question. Anyway, sorry, what I was going to say is there are these rows where all the numbers are odd. That arrow's not quite on screen. The bottom row, 1, 7, 21. The numbers are all odd. They seem to correspond to these points where the triangles stack up nicely. When do they happen? There's one here, 1, 3, 3, 1, and at the bottom 1, 7, 21. When's the next one? When does it keep happening? You might have an idea, you might have a guess, you might have a hypothesis, but maybe you could try and prove that, or try and explain to yourself why it's true. Explain to someone else. Every 3 rows is a great suggestion because there's one here at 3. I mean, maybe 4 because it's 1, 2, 3. So skipping 3. So your prediction then would be that the next row that's all odd would be down at 11 or something. Well, good news, 11 is odd, so it's a good start. Only one way to find out, right? It's just keep adding together these small numbers. The numbers get larger very quickly. A good trick, if you're only interested in even and oddness, that's called parity, by the way. If you're only interested in parity, then you might like to just keep track of whether the numbers are even or odd, because you know those rules, right, about adding together even numbers and odd numbers. Anyway, Denim's going to try prime numbers. That is brilliant. If you're watching this and you have a suggestion, like checking all the multiples of 5, like Marcus is going to try, or checking all the prime numbers, like Denim is going to try, you could do it now if you like, and tell us in chat what happens, or you could get a computer to do it if you're into giving instructions to computers. You could get them to try that, or you could do it on paper in your spare time. If you're watching the recording and you don't have access to live chat because it's not live, you could let us know on that email address. What I would really like is next week to come back and say, hey, look, people tried powers of 17 or whatever. A totally mad idea that came out of this stream is now reality. Good, okay. Next we'll make a 5-length triangle. It's a 5-length. The size of the triangle. How big's the next triangle? Brilliant question. A 5-length triangle. So you're sort of looking at the lengths. Right, yeah, look. So is this like the side length of the triangle? This is a side length 1 triangle. This is a side length 3 triangle, maybe? I think I understand your hypothesis. I think. If you circle the twin primes, oh my goodness. Okay, right. Square numbers, there's a triangle with a hole in it. Square numbers. Brilliant stuff. Okay, by the way, this is a fractal. Somebody said in chat it's a fractal, and the particular fractal that it is called the Sierpinski triangle. It's really surprising to me that Pascal's triangle contains Sierpinski's triangle. Somebody out there requested Sierpinski's triangle as their favourite triangle way back when we did favourite triangle facts a while ago. Here it is for free on bonus. Do the numbers with the numbers? What do they mean? Marcus tried multiples of 5 and 6. After a while, it is faster to get a computer to do these. Computers are pretty good at adding numbers together, checking whether things are multiples of 5 or not. Brilliant. Okay. So yeah, amazing patterns, but what do they mean? Maybe you're getting other fractals, or maybe you're getting other shapes. Okay. Cool. Do I get paid for live streams? The live streams are sort of part of my job. Sort of. I think I might be the only mathematician who's being paid for a job that involves live streams. Not very many people who get paid for live streams anyway. Right, okay. I want to tell you about robots. Really basic robots. Don't get excited. No sort of advanced AI is going on today. The most basic form of robot is something called cellular automata. Those are some fancy words that we're going to break down. Oh my goodness. Sorry, there's been a bit of a break in live streams. I've lost track of how to use technology. Good. Is Tom Crawford paid to do live streams? I should have to catch those. Oh yeah. Oh sorry, all of the students on the live stream. Okay, robots time. Cellular automata work like this. They have a string of cells. I'm going to use circles. And then there's some rule for how you get from one row to a new generation or a new row. So this is like row. Let's count from 0 since we're counting from 0 today. Maybe we'll have a new row. I'm going to draw my new row to make it look a bit like what we were just doing with Pascal's triangle. I'm going to draw my new row like this. Normally people use a square grid. I'm using a triangular grid. Sorry, everyone. And your rule might be based on how do you update these. So maybe some of these are coloured in and some of them are not. And there might be a rule for how the next row down depends on the previous one. And it could be anything. It could be really complicated. It can involve looking back at all of the data that you had in the previous state and adapting all of that data. Or it could be simple. There could be some simple rules for how this data influences the ones below. How these circles influence these circles below. This is like what we were just doing with Pascal's triangle, where we had some rules that were something like, if this means even and this means odd, then our rule might be something like 2 even numbers. If you see those, then underneath you get an even number. An even number and an odd number, they add together to give you an odd number. And your odd number and an even number, they add together to give you an odd number. And if you see 2 odd numbers, they add together to give you an even number. So we might have a rule like this that says, based on what you see above, here's the rule for what the next row down looks like. The reason I'm telling you about this is because if you're training a computer to do that Sierpinski triangle thing we just saw higher up, this is the fastest way to do it. Don't bother explaining even or odd numbers to your computer. Don't bother explaining adding or parity. Strip away all of the detail about what the numbers actually are and just teach your computer, well, the thing is that this row of data, and what I want you to do is, if you see 2 zeros or whatever, write a 0. If you see a 0 and a 1, just write a 1. If you see a 1 and a 0, write a 1. I will interpret it later, computer. You're great at doing these 4 different cases of what you might see and what you write down underneath. Yeah. So and the computer doesn't need to know that these represent adding. The computer doesn't need to know that these represent adding numbers together and taking the remainder when you divide by 2, which is kind of technically how adding together odd and even numbers work. None of that is really interesting to your computer. Just explaining to it, these are these 4 rules. So we can also think about new rules. I'm going to draw a different rule. Secretly behind the scenes, my rule refers to what happens when you multiply numbers. When you multiply numbers, you get something like this. No, what do I mean? When you multiply numbers, you get something like this. Can I at least do this correctly, please? There we go. I can do this. Yes. When you multiply numbers, you get something like this, which is a different rule about how to update things. So if I want to see what happens in Pascal's triangle if you multiply instead of adding, who knows, then I could explain it to my computer like this. Oh, and people are interpreting these in terms of like AND gates or OR gates. Computer scientists in the chat represent. Brilliant. Yep, okay. People, if you know about logical gates, you've seen something like this before. You have, in a way, learned how to wire your first basic robot sort of thing. The surprise, I suppose, is that this leads to Sierpinski, which is sort of wow, that something like this, wiring together a load of these XOR gates, to use the computer scientist word for what these are, wiring together a load of these XOR gates and feeding the results through, generates this kind of Sierpinski triangle of blinking on and off lights. So somewhere buried in this, there's a very interesting electrical engineering thing to go and build loads of XOR gates and to see them light up like a Sierpinski triangle. I'm not sure that's homework so much as a thought experiment. This other rule underneath is a lot less interesting. I think I got away with it, but I suggested out loud Pascal's triangle but multiplying instead of adding, and nobody called me out on it. You should call me out on it when I say something really stupid. The idea of Pascal's triangle but multiplying instead of adding is really stupid, because if you multiply instead of adding, we know what happens. The numbers are both 1. Sort of not an interesting triangle, James. Pascal's triangle but multiplying instead of adding is one of these things. It sounds clever out loud, but if you actually try it, it's not interesting. It's even worse with my computer implementation with this cellular automata thing, because my cellular automata can see all of these, can see a whole bunch of zeros outside. So it's sort of even worse. My computer can see loads of zeros outside, and it's going to multiply those, and actually it's going to multiply by 0 to get rid of all of the zeros, and my triangle would just die off like that. So you start with some data, and this rule just erodes it or dissolves. Dissolves data. So if you've got a string of data, then this rule just wipes it out until you end up with all zeros, which is a sort of interesting way that when you look at the rule, it's not obvious that the second one gives you dissolution and the first one gives you fractals. And there's this question then, I suppose, of what do all the other ones do? How about subtracting? Brilliant. I am so glad that someone said, how do you feel about what about subtracting? Negative Pascal's triangle. Ooh, what does negative Pascal's triangle mean? Is that where you start with minus ones and you add? Can't tell if that was clever or stupid. Let's do the subtracting thing. I have a variant on subtracting actually. I don't know why it started doing that, by the way. When I move, anyway. So variant on subtracting. Subtracting gives you lots of negative numbers. I find it a little bit hard to think about. So what if we do Pascal's triangle? I'm still adding, but start with 1 and minus 1. The minus 1 plays the role of some subtraction, if you like. I think this is sort of the same as doing some subtraction. So maybe put down your strings of 1s and minus 1s. If you've tried this before, then no spoilers. If you haven't tried this before, which I'm hoping is most people, down. Oh, go up, so like, oh, going down. Yeah, okay. Yeah, how do you know which way to subtract? Anyway, so start with 1 and minus 1. I'm going to keep doing this one. These numbers, I hope you agree, if I'm doing this right, these numbers are different. Hard question. What's going on here? What are these? What's going on? Is that a hard question? Yeah, I think I stand by that. I think this is a hard question. What are these? Pascal's triangle, subtract and then compare the negative and positive numbers. Okay, so I'm doing something that's a bit like subtraction, but easier for my tiny brain, which is to add, but using negative numbers. Some people really don't like negative numbers, and that's fine. That's an opinion you can have. Okay. Pascal's triangle with fractions instead. Sure. Pick your favourite fractions. I think. You'll then have some new questions about the fractions that you get out, or actually, is it even obvious you'll get fractions out? Depends what you do with them, I suppose. If you keep adding them, do you eventually end up with whole numbers? If you keep adding them, do you eventually end up with whole numbers? No. If you start with, I think that's not true, because if you start with 1/3, then you always get some things that are not whole numbers. Yeah, because it's Pascal's triangle divided by. I'm thinking out loud. I should probably let you do the maths instead. Hard question then. What's going on here? There is some annihilation going on, right? I like this picture because there's kind of these negative numbers on the right and positive numbers on the left, and down the middle are zeros. It balances out really nicely. There's something going on with, yeah, column of zeros down the centre. Due to this kind of annihilation thing going on. That is correct. Good pattern spotting. 14. Now what I almost said there was 14. I don't think that 14 appears in Pascal's triangle, which is incredibly false. It's just very false. 14 definitely appears in Pascal's triangle if I think about it for a second. There it is. But I still value the part of my brain, the quite large part of my brain that says stupid stuff like, is 14 in Pascal's triangle? Because it's trying to come up with questions. That part of my brain is trying to help, and sometimes it might come up with a good question, in which case, yeah, rewarded with serotonin, I guess. It says trying to add together 1 and 5 desperately on a live stream. Do the diagonals form sequences? Great question. I mean, everything's a sequence if you believe in it, right? But I suppose more seriously, Kai's asking, does that sequence represent something, or is there a formula for it? Is it nice? What's going on? Yeah, every positive integer appears in Pascal's triangle. Yeah, that is true. There's actually quite a dull bit of Pascal's triangle that I should have remembered that we didn't talk about with the diagonal. Is the first diagonal is the numbers. Good. What happens if you add that triangle to Pascal's triangle? I think I know the answer, but I also want you to try it. I think the answer is that Pascal's triangle plus this triangle is a different Pascal triangle. There's kind of a different variance of these you can do. If you're inventive and creative, then you're maybe already thinking about trying different numbers at the top or different rules. Just to wrap up, I've left you with some sort of homework here to try and explain some of the numbers that come out of this weird variant of Pascal's triangle, or to try and describe what happens for these rules with these cellular automata, or even to go back to the original Pascal's triangle and try and spot some new patterns, try and spot something else that's going on. So I spotted Catalan numbers. If you know what Catalan numbers are, then you will be excited to see them. If you don't know what they are, then you're in for a treat, because once you've generated some of these, you can look up the Catalan numbers, and then you've got a real challenge to try and learn about Catalan numbers and describe what they are. Catalan numbers will probably come back at some point this term. Who knows? I shouldn't make promises. Numbers in between the gaps. Whoa. triangle numbers to one-dimensional. Yeah, okay. I like that pattern spotting. Somebody's just described these, and they put haha, so I know they're joking, but they describe these as 1D triangles, which is a new cool terminology for a line of dots, I guess. And I think they're trying to describe this as a 0D triangle, which makes this quite interesting, I suppose, because it means that 1 is the only number that's a 0-dimensional triangle number and a 5-dimensional triangle number. Okay, right. I should really try and tone down the stupid part of my brain, right? No, we need it for doing maths. Yeah, there's some Catalan numbers in there. I don't have time to explain what a Catalan number is. I'm hoping that I can make them sound interesting enough that people go and look them up if they're interested. But people have spotted that people who know about Catalan numbers have spotted them appearing here. That's not a coincidence. So if you don't know about Catalan numbers, then we'll talk about them at some point, but homework if you want to have a look at them now, try searching for Catalan numbers. If you do know about Catalan numbers, why are they here? I mean, why not, I suppose, but also why are there Catalan numbers in my exercise? Just to wrap up, because we've got about 5 minutes, something I'd really recommend for this, if you're going to get involved in these cellular automata, if you're going to think about the different rules, let's quickly think about how many different rules there are. And here I mean rules like this. So rules where you look at the two circles above and you combine them. Doesn't have to correspond to addition or multiplication. You combine them to get something new. I'm now jumping around quite a bit, so chat's getting a bit. Yeah, so there are different logic gates. I guess my question is how many logic gates there are there, but that sounds like a very computer science sort of question, and it's a little bit. In order to engage with that question, you probably need to convert it into this. There are 4 different inputs, you see. There are 4 different cases about what could be going on. You could see 2 zeros. Your computer needs to be prepared for what's going on for those. You can see a 0 and a 1. You can see a 1 and 0. Or you can see a 1 and 1. I'm using numbers because I'm thinking about computer science now. I'm using numbers instead of colours. That's a bit clumsy, I suppose. 4 different inputs, and chat saying 16 possibilities for what you do for the output. Yeah, the rule can depend on the order. They don't have to be symmetric. So I don't know if your logic gates have to be symmetric or not, if they have to respect left and right being kind of interchangeable. But our cellular automata doesn't have to. There is an interesting rule. Sorry, this right clicking doesn't really work. There is an interesting rule that looks like this. Again, I don't want to tell you too much because I sort of want somebody, could be you, I want somebody to go and explore what's going on. There's a really interesting symmetry breaking rule which says, really interesting, might be overselling it, but the rule works like this. If you see one dot on the right, a black dot on the right of a white dot, then make the one underneath into a black dot. If you see a black dot on the left, white dot on the right, then just put a white dot in all other cases. If you see 2, then I think, what do I want there? I think I want, maybe I want that. Actually, I'm not sure what I want there to make this interesting. So maybe homework. Is this the interesting one, or is it the other one that's interesting? Are neither of them interesting? Maybe neither of them are interesting. Okay, so this is sort of an example. I don't know if that corresponds to a logic gate or not. I don't really know about logic gates. But I do know that it's a rule that I could teach to my computer. I could say, if you see this, do this. If you see that, do that. If you see that. It's a kind of it's a function, really, like a rule. Okay, so kind of press there. Okay. So I think I agree that there are 2 to the power of 4 of these. Because of your 4 possible cases, there are 2 choices about what you could do. 2 choices about what you could do in each of them. You can make independent choices, it really doesn't matter. If you are allowed to look at 3 inputs instead, so real big extension to 3 inputs instead, so maybe we're looking at all 3 things that are above, like the one, maybe use a square grid and think about the one that's directly above and the 2 that are next door. 3 inputs, then the number goes up quite a lot, and there are now 2 to the 8 different possibilities for how that function might work, because there are 8 different inputs. 2 to the 8 is quite a bit bigger than 2 to the 4. So if you explore these 16 cellular automata and you decide that they're not interesting enough, then you might like to look at these 2 to the 8. You can find out more on websites like Wolfram MathWorld. In fact, Steve Wolfram, who made Wolfram MathWorld and Wolfram Language, one of his big things was cellular automata, which are on the screen now. So it's sort of like it's not like addition. In a way, this new rule on the screen here is not addition either. I mean, it happens to correspond to multiplication, but when my computer's enacting this, it doesn't really multiply. It doesn't really need to know about multiplication. So in fact, I can set this to be whatever I like, and still I'll have something. Maybe it doesn't correspond to any sort of adding or multiplying mathematics. It doesn't respect symmetry between the inputs. But I get something happening. So this is sort of slightly, it separates the study of what do these cellular automata do as distinct from what's going on in Pascal's triangle. It's a sort of form of abstraction to take the concept of adding together numbers and abstract it to what happens if you just combine things, which is a very, very abstract way to go. B and not A. Right, okay, so I've got an opinion in chat about logic that is asymmetric in the inputs A and B. So that's nice. Thank you for that. I've forgotten everything I ever knew about logic gates. Should probably learn some stuff about logic gates as well. Oh, no, I'm learning history of maths on Aphantasia. Triangle with 3's down the side. Do you want 3's down both sides or 3's down one of the sides? I mean, the answer is almost certainly yes. You can do the triangle with 3's down the sides. So I think 3's down both sides gives you like 3 times Pascal's triangle. Everything's just like 3 times as big. This one, I don't know what happens. Like this? Yeah, I don't really know what's going on. Where are the odd numbers? Let's find out. So we've hit the hour. This is officially a 1-hour show. Thank you for watching. If you've got to go now, bye. Have a lovely evening. Both you get 3 times Pascal's triangle, I think. Everything's just 3 times as big. One-sided, I don't know. This is officially a 1-hour show. If you've got to go, then I'll see you around. I'm going to hang out a little bit just to see if people are suggesting stuff to do with Pascal's triangle. Oh, it's kind of not. I thought it was going to do a Sierpinski thing, but it's not done a Sierpinski thing. It should just be a Sierpinski because the adding... Oh, is it 2 overlapping Sierpinski triangles? It's the same sort of mechanism as Sierpinski. Yeah, here we go. It's going to be a bit like Sierpinski. I'm circling odd numbers. It's going to be exactly the same. Thank you, chat. Yeah, okay, good. Because the actual numbers don't... Okay, this is an example of where I thought I was being clever, but I was doing the same thing that we'd already done. This is the same calculations for odds and numbers. Oh, do these other patterns serve any purpose, though? So, being able to spot patterns is a good skill. It's just handy in life to be able to understand the world around us. In particular, these cellular automata are really interesting because they can do complex behaviour from very simple rules. That's a big theme in things like emergent behaviour and looking at how do flocks of birds work together to coordinate how the hive's moving. If you have lots of tiny nanorobots, can you get them to achieve a task that's disproportionate to the size of your tiny nanorobots? Can you have simple rules that generate complex behaviour? They also turn out to be related to chaos theory, which is one of my favourite things, where you have simple rules that generate really complex behaviour. And that links back to something someone had said earlier, that interesting but really confusing. These automata are another case of deceptively simple things that are interesting and then turn out to be quite confusing. They do quite complicated things. So these are the robots I'm claiming. They behave following some rules. You can... they're really stupid because they're following very simple rules. You can, if you get really into this, put them onto 2D grids or something and interpret them more as the ones are actual physical objects. I guess here it's kind of like soup, that they're all moving around and cancelling out. But you can have rules that represent things that start to look more like an ensemble, a collection of moving objects. Something to look up if you get really into these things is Conway's Game of Life. Conway's Game of Life is Okay, tick off your bingo cards. Conway's Game of Life is a bit like this, but in higher dimensions, because it uses a 2D grid of cells that are either ones or zeros, and it has some rules about how that updates every second or every time step, whatever, maybe every millisecond or something. The behaviour you get out is incredibly lifelike, incredibly weird, incredibly complicated. The rules are really simple, the behaviour is really complicated. Some people think that this is some way of joining up mathematics and biology, that this might be useful in our quest to try and explain biological phenomena using mathematics. Maybe. Early days. But I like to say that maths has already done quite a good job of helping out physics, doing quite a good job of helping out chemistry, and is currently doing a job of trying to help understand some biology stuff. Good. What's my definition of stupid? I should probably not have said stupid robots. I don't think I ever... So my definition of stupid is not going to be very good, right? Because I've used it just now to describe robots that are following extremely simple rules, but generate Sierpinski's triangle. That's not a stupid thing to do. So maybe there's hope for all of us that even doing very simple things, we can contribute to something large and complicated and beautiful. Right, okay. I didn't hurt the robot's feelings. They don't even really exist. Marcus's generated an upside down triangle. It went really... I think I'm quite keen that this term on Math Club we generate new stuff, even if it's rubbish. Generating new stuff is something that mathematicians have to do all the time, that maybe in school you don't get to do enough of. Because in school there's lots of time for learning lots of things. Anyway, this is not a rant about schools. This is an opportunity to be creative. The downside of inventing stuff is that sometimes you invent useless things or terrible things, like my triangle full of wands. That was not a highlight of today's stream. I even erased it. Oh no, it was over here. Triangle full of wands. Not useful, right? But maybe it could have turned out to be good. Who knows? I want to finish with a quick ad. Not sponsored, just another recommendation. If you like maths live streams, you might also like the Parallel Circles project. They're doing live streams on Tuesday and Sundays, so you could get 3 live streams a week if you liked about mathematics. I think I'm going to call it there. Thank you very much for joining in and all the suggestions about triangles. I can't wait to see what people send in or suggesting comments or live chat about other Pascal's Triangle-like things that they've invented, or patterns with all the powers of 17. Interesting to discuss theories and theorems and discoveries of maths and applications. Cool, right, okay. More live streams also exist, but they're not this one. That sounded like a weird reverse endorsement. Anyway, I'm going to call it there, and see you next week in 167 hours for another episode of the Oxford Online Math Club. Bye. How do I turn it off? Oh no. Thank you, Catherine. Thanks, Sierpinski person. Oh, I'm glad that Sierpinski person saw that Sierpinski triangle. Goodbye, random people. Yeah, and see you, Marcus. Right, good. Oh, hi again, gals. Bye, gals.